Our next speaker will shed light on the exciting possibilities of quantum computing. Dr. Murthy Rallapalli has more than 20 years of experience in designing, selling, and delivering IT technologies, strategies and transformation solutions for corporate security and privacy, mobile services, and cloud solutions. He is a professor at Augusta University and is the Quantum and University Ambassador for IBM. He has also been very active in the planning of this and previous big data and analytics education conferences. Please welcome to the stage Dr. Murthy Rallapalli.
Good morning. Welcome. And first of all, thanks for the organizers, Dr. Elena, for the invitation. What I'm going to talk about is the quantum computing. Out of curiosity, how many of you have heard the word quantum computing? Okay, very good. How many of you have some hands-on programming on quantum computing? Okay, that's good. So the limitation is extremes are like this, which is fine. I'm probably not too much different from you. First of all, quantum means a lot of different things for a lot of people. So let me just level set what is quantum computing. When things become really short and small, the bizarre world of quantum mechanics kicks in. Now, when I say small, how small are we talking about? So today's transistors, which makes our computing possible, they run around 14 nanometers, which is the same size as, close to the size of a molecule. But when these transistors start becoming smaller and smaller to the size of atom, that's where the bizarre world of quantum mechanics kicks in. Now, what is bizarre about quantum mechanics? How many of you have physics background? Okay, very good, very good. I don't have a physics background other than I have electrical engineering and a PhD in computer science. But quantum computing is something I've been playing around for the last couple of years. And I think Todd was asking a question earlier, where is machine learning in future? My personal opinion is the machine learning using quantum computing capabilities seem to be gaining a lot of traction. The problems like optimization, for those of you who are familiar with the traveling salesman problem, a salesman goes to X number of cities. The problem is trying to optimize his or her time without duplicating the same city. So quantum computing seems to be solving these kind of problems beautifully. All right, let me go ahead and see how I could somebody help me out, do I? Yeah.
It should be this.
Thank you. All right, I got 30 minutes. I got a lot of things to cover, so I'm going to skip some. Let me cover quickly the basics of quantum computing. So in the history of quantum computing, there are certain things that happened that changed the course of history. Particularly, I think Dr. Cox was mentioning earlier, there was a picture at MIT. He had shown a similar picture of IBM and MIT physicists got together in 1971. There's a very famous picture. I didn't bring it in on purpose, but that's 1981. That's one major event that happened. But in last couple of years, starting from 2015 to 2017, is probably where the quantum is reaching the common audience and the scientists in a way that we could actually explore and play around with the technology. In 2017, IBM launched this universal quantum computing. Where we are today is not universal quantum computing. Where we are today is what we call a NISQ computing, NISQ, noisy intermediate scale quantum technology. That's where we are today. Where we will be going is there are a lot of competition. There is a word called quantum supremacy and quantum advantage. The companies and the nations are all fighting it out. So we don't know who is going to be the winner. But it's an exciting time to be a quantum computer scientist, not necessarily quantum physicist, which always existed. But bringing quantum mechanics into the IT is very exciting time we are living through. Now, what is the difference between quantum computing and classical computing? When I say classical, the laptops that you're using, the iPhones that we are using, and all the bits and the bytes that goes behind these machines is what we call a classical. So in the classical, we have 2 bits, zeros and ones, right? When you present some voltage at a certain level, you call it as a 0 and 1. Now, I take a coin from my pocket, and I just throw it into the air. And I ask you to guess, is it heads or tails? So some of you may guess it heads, some of you may get it tails. But we would know exactly what the value of that coin is only when you observe it. Until then, whatever answer we give is a probability. The probability of being a heads is 50%, tails is 50%. In the bizarre world of quantum computing, until the state of what I call a qubit, in classical we call bits, in quantum it's qubit, it all goes by probabilities until the time it is observed. It's a very bizarre when the items that you're working at a very, very small level. That made Einstein crazy, and he actually used the word, the spooky action at a distance. In classical, we use binary. The quantum computer has 3 properties that makes it unique. One is quantum mechanical phenomena, but 2 other factors called superposition and entanglement. This is what makes quantum what quantum is. It is what differentiates quantum from classical. It is the branch of physics relating to very small. I think I already mentioned that. In quantum mechanics, the objects exist in probability, meaning Einstein actually made one statement that just because I'm not observing doesn't mean the moon does not exist, right? But when you talk about the very small, it's extremely probability. Only at the time of measurement you know the exact state. For those of you who are interested in the famous Schrodinger's cat experiment, I'd like you to go back. I don't want to repeat that. You probably heard it a million times. So there is also a probability of a small atom or a photon existing at the same place multiple times that led to the probability of the teleportation as a possible application. Now, a famous physicist, Dr. Richard Feynman, once famously said, if somebody says he or she understands quantum mechanics, means he or she does not understand quantum mechanics. It's an extremely complicated subject dealing with probabilities and some bizarre phenomena. And you measure a million times, you get exactly unguessable probabilities, proving that the physics that we know, how the planets work, and the reality that we see does not exist in quantum mechanics. Now, if we can capture and leverage this energy and the technology and bring it into the computing realm, maybe we can do things better and faster. So I'll give you an example. So let's take a deck of cards, and I took 4 cards from a deck. For argument's sake, let's say 10, king, queen, and jack, right? 4 cards. So I asked you, and I just shuffled it, and I asked you with a classical computer, can you tell me, without looking at it, which position is king? So you take 1 card and check, is it king? Yes or no? No. Okay. Next one. king? Yes or no? No. Oh, maybe it's king. So the number of permutations you've done is maximum of 4, right? 1, 2, 3, 4. And you may have hit it at the first time. But if I do the same problem to a quantum computing, the quantum computer looks all 4 values at one time and picks up, this is what you're looking for. So that's the difference, right? The linearity of the calculations is a completely different in the quantum world. So all the values exist and computable. I think I talked about the bit versus qubit. The only thing I want to talk about, the qubit is measured the state of a qubit. So it's a little bit complicated. The bit is zeros and ones, right? Qubit is measured in what we call a Bloch sphere. Bloch is the name of a German scientist. That is the circle that you see. If the state of the qubit is 0, right? It's at the north pole. If the qubit happens to be at the bottom of the Bloch sphere, then the state is 1. It's a 0 and 1. In addition, a qubit can exist any part of this Bloch sphere. That's where the probabilities come into the picture. If it is not at 0 and 1, if I want to calculate the state of a qubit at any given point of time, the formula is alpha, what we call a ket 0, that is you see the bar and the greater than ket 0, plus beta ket 1. This alpha and beta are complex numbers. For those of you who are not familiar with the linear algebra, complex numbers are real imaginary numbers like a plus ib. I is equals to something like a square root of minus a negative number, right? You cannot solve a square root of a negative number, but it's a complex imaginary number. So those kind of calculations go into quantum mechanics. Now, I mentioned in quantum mechanics there are 2 areas. One is a superposition, other is the entanglement. So let me just touch upon what a superposition is. The probability of a qubit existing in both 0 and 1 at the same time until the actual measurement is made is the concept of superposition based on. In case of a classical computer, a 1 bit can be in 0 or 1. Remember the playing cards example I had given you. In case of a quantum computer, a 2 bit can have 2 to the power 4 possible combinations, and you're not computing linearly. You're going through all 4 at one time, right? You can see the calculated. So what that means is every time I increase a qubit, the power of a computation is going to go up by 2 to the power n. Now, if it is so easy, then why can't we just make a 100-qubit machine? But that's where the limitations of physics come into the picture. So one of the problems with the quantum computing is what we call the noise and error detection levels. For the quantum computer to work, I mean, there are many companies do different technologies. IBM and Google uses something called a superconducting technology for generating the quantum bits and the quantum qubits. So the temperature has to be brought so low, lower than, I think it's 0.15 millikelvin, that is lower than the outer space. Only at that time, the entanglement action takes place for a very short period of time. During that time, the computations have to take place. So the complexities of physical hardware as well as the technology complexities, the noise, are extremely challenging. For those of you who are not familiar with the superconducting, it is the electricity passing through almost zero resistance. If you bring mercury down to a certain very low level and pass the electricity in a loop, scientists have proven that the electricity keeps on going forever. They've been doing that for years just for the experimentation. So that's the kind of environment the quantum computers need to be built. So this is just the table to illustrate the superiority of the qubits versus bits. Once you reach the level of 64, the quantum storage is, it's unimaginable, right? It's too big even to comprehend. So the storage capacity plus the compute capacity significantly goes up. Now, the other property I mentioned is the entanglement. We all know that Einstein mentioned that there's no object in physical universe that can go faster than light. Right? We all know that, and Einstein said it must be right? But when it comes to the quantum computing, when two particles are in an entanglement state, now what do I mean by entangled state? If you produce two qubits from the same source, if you happen to observe one qubit state, the other qubit always tends to be in the opposite state. If it's the ket 0, the other qubit is ket 1. This is proven that even if these qubits are at a great distances, there's a Chinese government, or Chinese labs have done some experiment with the satellites. They've done it unimaginably long distances. They proved that. And theoretically, it's proven that these two qubits can be at other ends of the universe. They exhibit this kind of property, which is, again, bizarre properties of quantum mechanics. If these qubits are somehow able to communicate at the time this entanglement happens with such a great distance, then what happens to the speed of light formula, the proposition of Einstein? That is completely broken, right? And that is proven now. You do it any number of times, this experiment. The entanglement happens. You increase the distance to any limit almost instantaneously. There is no time difference that is captured. Now, what does that mean? Just because these particles are entangled, how does that help us, right? So that's where, if quantum has a PhD, this is my opinion, the world is somewhere around 5th grade. I'm probably in kindergarten or something. So but theoretical applications that this can be proven are out there. The number of papers are out there. Shor's algorithm, if those are familiar, are out there. 98% of our web traffic on encryption uses 256-bit encryption. The power of the encryption comes from what we call a factorization. For those of you in cybersecurity would know that if I give you a number 10, the number of factors is 2 and 5. If I give you a number 2 to the power 256, can you give me a factor of that number? So no current classical computers can calculate that number in a reasonable amount of time. And that's what we take advantage of in our encryption. And 98% of our encryption works that way. But theoretically, it is proven that if the quantum computer of X number of qubits become available, that can be broken very easily. So what does that mean to our future world, right? All encryptions, the banking and emails, everything. So that's why there is a sudden rush. Now, should we be worried that my bank account going to be unencrypted tomorrow? Probably, definitely not. 5 years from now? Definitely not. 10 years? Maybe. So that's where we are. But this is an exciting time to be getting involved in quantum computing. And there are a number of universities around the world, including North Carolina University, and they're all going with IBM and introducing these quantum computing courses, and quite a few in Europe as well. As part of this, there's something called an IBM Q experience. I'll talk about it in a minute, but let me finish up these things. So it's probably some of these are a repetition. Every time you double the transistors, the classical computer's power increases. But when you increase the number of qubits, I think I already mentioned, the power goes by 2 to the power n. Now, the question always comes up, what qubits do we have today, right? Are we 50, 51, 70, somewhere around that range, depending upon who you ask. There are some companies who claim they have 200 qubits, but the question is not the number of qubits. The question is, what is the error detection level, right? I could have any number of qubits. If their error rate is very high, it's not going to serve my purpose. So that is actually a quantum computer in IBM Watson Research Laboratories. So 2 to the power of 50 is the IBM Q system with 50 qubits that are available today for some of the commercial clients. They probably have much higher than this in the laboratory environment. But if ever we reach the level of 275 qubits, there are more basis states than there are atoms in the observable universe. So that kind of tells us the power that we are going to experience, hopefully in our lifetime. Now, how does these beautiful machines work? That's an actual, the chandelier-looking picture is actual quantum computer. So as I mentioned, you have to introduce a photon, which is a light particle. So a light particle is both a particle as well as a wave, right? It's been proven, for those of you familiar with the double slit experiment, it is proven. So you send this photon through this chassis and reduce the temperature. When your temperature is reduced to 0.015 Kelvin, which is very cold, I would never put my finger in there, and kind of hit it with some microwaves, that's when the action starts. The qubit starts generating, and things start happening, the computations. You have a very small range of starting your computations. I'm going to skip this superposition and entanglement. We already talked about it. If I were to summarize what differentiates quantum to classical, these are the two things I would talk about it: superposition and entanglement. In layman terms, the probability of having two states at the same time, probability, right? The reason why I'm saying probability is until you measure it, you never know, right? Schrodinger's cat equation. Entanglement is how these photons are correlated with each other, independent of the. If I look at the state of one qubit, it could be independent, but it cannot be independent of the state of the other qubit. They're always entangled. This entanglement is possible, as I mentioned, regardless of the amount of distance they are at. I think I got about 5 minutes. I'm going to skip some of these the slides. So what's coming, right? What's the future looking like? The quantum chemistry optimization Shor's algorithm, the years to advantage is 10 to approximately 10 to 15, if possible. Now the question comes, if we are that far away, should we be concerned about it, right? So, and the answer is, this is the time to be concerned and start learning about it, because that's where probably the whole world is going to be. In early 1900s in the United States, 68% of Americans were in agricultural industry. And today, it's only 3% Americans are in agricultural industry. But the output of agriculture today is 3,000 times more higher than what we did in 1900s. This is all because of the exciting technologies that happened. So this is going to be one of those exciting things. So I'm going to take one more slide, and then I'll open up for the questions. Where are we on the quantum journey? The quantum itself is kind of siloed into 3 silos: quantum foundations, ready, and quantum advantage. Foundations is probably 1900s, where beautiful articles came up. There's something like a Bell's inequality theorem, etc. And the quantum readiness is the actual algorithms. So today, you can actually do the unstructured data classification by quantum computer, at least in an experimental lab that's available. And quantum advantage is where the problems that the classical hard problems are quantum easy problems, like an optimization, traveling salesman. That's what we call a quantum advantage. Quantum supremacy is when you can easily solve the ones that you cannot solve with the classical computer. So I'm going to take 1 minute on the sophisticated deep learning and quantum. These are all theory, right? These are the possibilities with quantum computing once the sophistication gets available. Simulation, optimization, boson sampling is the probability of the distribution. To be honest, I'm not an expert in boson sampling. My research is mostly in the area of optimization and the machine learning and the deep learning using the quantum at a 5-qubit level, and I do have access to the 50 if I have to. So let me stop there and see if there are any questions. No question is a small or a silly question. Please ask all kinds of questions.
Any questions for Dr. Rallapalli? Here comes one. First.
Hi, I think everyone knows me now. So I'm really curious about, are we making in the U.S. the investment in this technology and in the research? Because I know some other countries are investing quite a bit and would like to get the lead here. So how do you see the investment in the U.S. in particular?
So in the U.S., the government labs like Sandia National Laboratories, like in Tennessee, there's a Sandia National Labs. They are doing some good work. But in the U.S., it's led by the private industry. So in my opinion, no bias, but IBM is the leader. Google is doing a great job. There's a company out of Toronto called D-Wave. They're doing a good job there. But on the international level, I feel that we are still winning the game, quantum, which is a good thing, right? But the policy needs to be there, right? We can come up with the beautiful solutions, but there's a governance and the policy at the public government level should be there. In my opinion, I think it's going in the right direction.
Any other questions?
Great presentation, by the way. So I thought I'll just ask a silly question. By the way, I'm Lanesh. So I think I heard you saying that if your account had to be decrypted, maybe it will take at least, maybe not 5 years, but 10 years. Did you say that because you think the skills required or the power that's required or the technology that's required is going to take that long for anyone to kind of do that or get into that?
Right, it's a good question, Dinesh. I think the challenge is at the physics level, reducing the temperatures. So the problem today is the qubits we can create, but the amount of transient time that qubits can remain in the qubit time is at a microseconds level. During that time, we have to do the computations, right? Unless that time is significantly improved where we can reliably do the calculations, it's going to be far off. So the problem is that the physics, the hardware challenges, but we made a significant progress, so we're still waiting for the breakthroughs in the quantum era. So 5 to 10 years is fairly optimistic, but who knows, right? Certainly some new innovation may come up. Yes, ma'am, do you have a question?
This is the final question.
Just a quick and simple question. Is the benefit really the speed? Is it the application, all of the above? And if, let's say it wasn't around, is it the current computing can be used, but it would just take a very long time to get to the same answer?
That's a very good question. A good friend of mine from Stanford once mentioned that speed is not necessarily the biggest advantage of it, but the benefit is the ability to study the multiple states at the same time. For example, if you take an atom and hydrogen, right, with very few number of protons, and but once you increase to helium, not helium, caffeine atom, for example, where you have 12 atoms going around the nucleus, how they interact with each other, how these electrons are interacting with each other, also interacting with the nucleus, there is no way we can compute that today. Our ability to compute that level of calculations stops once you have more than hydrogen. So its ability to study the multiple states at the same time, that's a significant quantum advantage. There is a speed advantage too, but I wouldn't look that as the number one advantage. So hopefully you all learned something about quantum computing. It is available for anybody to learn. Quantum experience, you can actually learn. The programming is called Quasm. Just like Python we are used to, you can do a hello world in a Quasm computer. It's a QASM. It's an assembly kind of programming. So those of you got some interest in quantum, I'd like you to start looking into it. I'm pretty sure that's where the future is going to be. Thank you all.